Welcome again to the continuation of our case with sequencing jobs in a flow shop with two stations. We discussed the fact that this particular solution could be attractive or would be what the human being would try to solve using his or her common sense on how to optimize the performance of the flow. However, we have developed, or I have developed, a very simple algorithm in which what we do is we flip the pairs of these jobs in such a way that if we reduce the number of the total lateness after computing the complete sequence, if the total latency is reduced, then we keep that change, and if it's not, then we go back and undo the change and explore another pair. So let's execute that, and for that I have prepared a different region just underneath with the same titles. So here we have exactly the same table. We have exactly the same data, it's just that it's randomized, and let me execute the code. At the beginning we start with 253, but as you can see that the code is exploring, making pairs, and it's harder and harder every time to find a new, better solution, and that's why it's taking longer to reach an even better one. In this example, I am computing 1,000 times these changes of pairs, trying to obtain a better solution. And after I run it, the total value that we achieve is 196, and we reduce the number of late jobs from 15 to 12. Now, there are a few jobs that actually get worse naturally. In this case, job number 7 and job number 17, job number 10, or ID 10, is the total latency is 79. So some of the jobs actually get hurt, but as total we obtain a better performance from 253 to 196. So these wouldn't be easy to identify or very fast to compute. We have to do this by hand, and in many jobs, in many working positions, a lot of people are using in practice these common sense decisions, like let's order everything by due date. And there is a potential benefit of exploring alternative solutions to these type of problems in everyday small tasks that usually are not involving a computer program, and still we're not doing the best that we can. Is this the best solution that we have with 196 units? Maybe not. We cannot know at this point. Maybe we can improve it further. And there are other algorithms that we could use. In this case, we have used a greedy randomized algorithm, but we can do a totally deterministic algorithm, and that is because the number of pairs that we can exchange with every particular solution is limited. We have 15 jobs, and we can compute the number of possible pairs that we can start. If we compute how many combinations we could have with these 15 combinations, if we select 2 at a time. So if we can select 15 in the first for the first case, once we select that one, we can select other 14. That means that we can have 15 times 14 um, solutions that we could explore at any particular point. And there is no reason why we should just randomly select one of them and see if that's good. What we could do is run all those 15 times 14, which is 210. We can run these 210 combinations and for the current solution, and select the one that has the better performance, the best performance. And based on the best performance, we select which one is the one we want to keep, and not consider all the others. And now we have a new starting point. And from that new starting point, we select the 210 combinations from that new solution, and we select the best one, and we go to the next starting point. And the benefit of doing it like that is that at least we still cannot guarantee that we're going to have the best alternative, but at least we would know when to stop, because we would know that if for a particular alternative, after considering all the 210 alternative solutions around the current solution, what we call a neighborhood of 210 solutions, by flipping two jobs in their sequence position, if all these 210 alternative solutions are worse or equal to my current solution, then I don't have any motivation to continue, because given the current solution and the neighborhood I have, there is no benefit of keep exploring, and we will be done. This is very computational intensive, whereas the method that I use here, it only ran 1,000 times. In the other method, it would run 210 times for each solution, intermediate solution that it gets. But again, neither of these two methods, I cannot promise that any of the two is better than the other. It's just a different approach with different philosophies. One is let's take what we can as soon as we can with a randomized step. The other is more the procedure is more carefully written, in the sense that we're only going to take a step if it's the best that we can take at the current moment. And still, given the fact that we could be trapped in local optima, it could be that we will not be able to find the best solution in this way. We still have the challenge of escaping the local optima. And think about it: if we are using this deterministic solution in which we explore the 210, every time that we start the process in the original solution that we had with the due dates, assuming that due date is a good starting point, the sequence order by due dates is a relatively efficient starting point of the algorithm, then every time we run it, every time we're going to get exactly the same solution, and we are not going to be able to escape local optima. We still need to find algorithms that allows us to explore other solutions that are probably farther from the original starting point, with the due dates starting at as a sequence arrangement, or the criteria for sequencing the jobs. And maybe there are other solutions that are better than this one. I have later found that I made a mistake in my code, and therefore the correct answer is not 253 units of time, but 211 units of time, and the number of jobs late dropped from 15 to 13 only, but still there is some improvement. So thank you.